so you might have learned this before in your previous class, the rule that all students take calculus. Okay, that rule, if you've heard anyone say it, doesn't mean that all students actually take calculus. It's a way of remembering what is positive in which quadrants. So instead of teaching it to you, I had you try and figure it out, especially if you had never done this before. Maybe it'd be more valuable to figure it out on your own. So hopefully you drew something for each problem. Maybe you drew like a little quadrant 1 angle here, and maybe some random point. And although we don't know what point this is, it is definitely in quadrant 1, and we know that its x-coordinate is positive and its y-coordinate is positive. So if this is the unit circle, and the radius is 1, you can tell that cosine and sine are both positive, right? Okay, that's just because x and y are positive respectively. So we would go ahead and respond that this is positive. Why is cosine positive? Because x is positive and x is cosine. Okay, let's go to quadrant 2 and draw a random point. The coordinates in quadrant 2 are negative, comma, positive. That's the way quadrant 2 works, right? So if that's the case, and your angle A is now here, if you were going to be finding tangent, you would be dividing y and x, and dividing a positive over a negative would give you what? A negative, right. So y over x gives you a negative ratio. If you're in quadrant 3, your drawing would look like this. There's your angle. There's your point. Both the coordinates are negative. So cosine is negative and sine is negative, but tangent's actually positive, right? And then cosecant would be negative because sine is, and secant would be negative because cosine is. But cotangent would be positive because it'd be x over y, and you would get a negative divided by negative, which is positive. So in this quadrant, cosecant would behave the exact same way sine does, and it would be negative. And lastly, quadrant 4, this would be your angle, A. You'd be somewhere out on the unit circle, right? The coordinates are positive and negative, but notice that x is positive, which means cosine is positive, which means secant is positive, right? So we would have a positive there. So some of you might have seen the rule, all students take calculus. Here's what it means. It just means that in quadrant 1, all things are positive. All trig functions are positive. But in quadrant 2, only sine theta and cosecant theta are positive. And in quadrant 3, only tangent and cotangent are positive. And in quadrant 4, only cosine and secant are positive. Okay, so we can tell from the xy coordinates plus, plus, and minus, plus, minus, minus, and plus, minus, which are positive and where they're positive. Okay, so some people just memorize it this way. A means all things are positive in quadrant 1. S means only sine and its reciprocal are positive in quadrant 2. The T here is, in the acronym all students take calculus, it's the take. And it means that only tangent and cotangent are positive there. And C, in the acronym it's calculus, but it's meaning that cosine and secant are positive in quadrant 4. Okay, so all students take calculus is how some people memorize it, but ASTC really means all trig functions, sine and cosecant only, tangent and cotangent only, and cosine and secant only. That's what it really means. Okay, so why am I giving you this? It'll save you a little bit of time thinking on my exam. Okay, so on my test, if I say something like,
Sine theta is greater than 0, cosine theta is less than 0. Which quadrant is it? You would have to maybe think about that. Well, the first statement is saying that sine theta is positive. So that means it couldn't possibly be talking about these two quadrants, because sine theta is negative in those two quadrants. But then on the other hand, the second statement says cosine of theta is less than 0, so it couldn't be quadrant 1, right? If it was quadrant 1, cosine theta would be greater than 0. So we can rule it down to, this is definitely a quadrant 2 angle. Has to be a quadrant 2 angle. In quadrant 2, sine is positive and cosine is negative. It's true. Okay? How about this one? Cosecant of theta is greater than 0. Cotangent of theta is less than 0. A little bit harder when you look at it that way. So what I would do is draw this and try to narrow it down. Cosecant is greater than 0. Can someone tell us which two quadrants that would mean? What do you think, Josh? Put your hand up. Yeah, Josh. 1 and 2. Right. Because if cosecant is greater than 0, that implies that sine is greater than 0. Right? Okay, so we're dealing with quadrant either 1 or 2. Here's our statement about a negative. Cotangent of theta is negative, so it couldn't possibly be quadrant 1. So again, this is quadrant 2 as well. This takes a little practice to get used to, but it does help you in the test. You can narrow it down to one quadrant. How about this one? Tangent theta is greater than 0. Cosine of theta is less than 0. Try that. Give it a try. It doesn't help anyone when you shout out the answer. It takes all the thunder out of their calculations and thinking, and it just basically puts them back to square one with not understanding the material. Okay, it happens every time you shout out an answer. Everybody needs to perform well on my tests. Class average of 65 isn't that impressive. Okay? We need to all be ready. Okay, tangent's positive, so it has to be 1 or 3. Cosine is negative means it can't be quadrant 1. So your answer is quadrant 3. Okay? Just a simple little exercise, but it does show up on my test. Another thing to memorize. Okay, you guys didn't have any homework last time. I was going to ask you any questions, but you probably don't have any questions at this point. All right, you'll see that the assignment I put on the board is only 4 problems, and the reason is it's graphing, so we have to make sure that we use graph paper and do the graphs real nicely. So, yes?
I don't think you put homework on this.
I might have forgotten. So let's do that now. Okay, so 5.4, I usually start this off with just like a little demonstration to convince you of something. It's not a big shocking revelation, but it's probably not something you've thought of before, maybe. So let's just say that I started drawing, let's say that this is my classroom, okay? And Mr. Shore is standing up front. Okay, I've got a marker in my hand. Let's make it a red marker. And I'm just drawing this circle. I'm just going around and around and around and around. Just drawing a circle. Okay? And I do this for a while, and you start kind of giggling. You're like, okay, Mr. Shore's gone crazy. He's retracing a circle like 1,000 times. Just going around and around. And suddenly, in walks Mr. Howard. Okay, so Mr. Howard comes in from the side. He's a lot taller than I am, evidently. You guys see my arm going around in a circle. I'm drawing in a circle, drawing in a circle, drawing in a circle. When he walks in the door, that is not what he sees, right? Because while I'm doing this with the marker, you clearly see a circle, but that's not what he sees when he walks in, because he comes in from the side of the room, and he sees it at this angle, and he doesn't interpret exactly like up and down oscillatory motion. You cannot tell the difference. If there's a light bulb on a bicycle tire, coming down the road at night, so here's a bike, don't laugh, okay, handlebars, okay, here comes a bike, it's nighttime, the only thing that makes the bike visible is a little red bulb on the tire, a reflector or something, and it's shining. If you were standing in a position where you're looking at the bike from the angle you are now, you would see that red thing going around in a circle. But if you were standing over here and it was coming at you, all you would see is a little red light going up and down, right? You couldn't tell if it was going in a circular pattern. How would you know that? It'd be kind of hard to tell anyway, okay? So is there really a difference between an object traveling around in a circle and an object swinging back and forth as a pendulum? Or is there a difference really between the idea of the Earth going around the sun once a year, or simply maybe a large plate of the Earth moving back and forth once per year? Back and forth motion, circular motion, they're not really that different. Okay? Okay, so then Mr. Shore decides that he's getting tired of drawing his circle, so Mr. Howard's already left. He decides that he wants to draw the circle and walk at the same time. So he decides, I'm going to draw the circle and walk at the same time. What's that going to look like? Well, I'll demonstrate on the board, and then I'll draw it on the projector. But this is what happened. I was drawing circles, right, originally. But you can't really tell that apart from this from certain angles, right? But if I'm doing this and I start walking, what happens? I get a wave. Isn't that true? So if I add a dimension of horizontal motion, something perpendicular to the direction I was originally oscillating, oscillating up and down gets translated into the forward dimension, it looks like a wave, right? So my drawings would begin to look like this. This is more important than you might think. It's just kind of a silly exercise and demonstration, but what it tells us is that when something moves back and forth, or in a circular motion, or like a wave, they all are basically the same phenomenon. They all repeat themselves either by returning to its original position, or something repeats over time. Okay? So any motion like this is called periodic. Periodic. All right? Okay. So enough of that. Let's go on. I want to show you something from a website that I found here real quick. So let me pull it up. Okay, so what we have here is an applet. It's like a small program. And it's just straight off the web. And what it's going to do is, as I move this point here on the right around the unit circle, you can see this is a unit circle. It's got radius of 1. Okay. As I move this point around the circle, the computer is going to try and help me keep track of the angle I'm at and the y-coordinate of that point as I move it around. Okay, so right now, what would you say the y-coordinate is? My point is right there where the arrowhead is. What's my y-coordinate? 0. Okay. But if I were to go to, say, 30 degrees, what's my y-coordinate? Look at my y-coordinate. The y-coordinate of this point. What's the y value? 0.5. Right. Okay. 0.5 it is. Let me keep going. Now I'm going to go up here to 90. What's my y value going to be when I reach 90? 1, obviously. I'm at the highest point on the circle. Okay, and then I can go on, and let's try to go on to like 150 area here. 150 is interesting. Here I go. I'm going to 150. My y-coordinate has returned to 0.5. I'm at 0.5 again on the y there. See? Okay. Next up is 180. At 180, I am back on the x-axis where my y-coordinate is 0. Right. And if I go to, let's say, 210, what's my y-coordinate now? Negative 0.5. We're all looking at the same thing, I hope. Looking at the little dot right here and asking what is the y-coordinate right now. The angle's 210. The y value's stop is 270. That's the bottom of the circle where my y value is. -1. Next stop is the angle 300. I'm sorry, I meant to say 330. At 330, my y value is -0.5 again. And when I go full circle, that's 360 degrees. I find myself back in the same spot I was when I started, where my y coordinate is 0. Okay. So while we were doing that, the computer was tracking out the y coordinate and tracing a curve. Only on this graph on the right, the x-axis represents the angle that I was at when I was rotating, and the y value on this represents the y value on the left. Okay, so the y value of the point is also the y value over here on this graph. So you can see how the x-axis is labeled 0, 100 degrees, 200 degrees, 300 degrees, and so on. The point, remember, went basically from a height of 0 to a height of 0.5, to a height of 1 to a height of 0.5, to a height of 0 to a height of -0.5, to a height of -1, to a height of -0.5, and finally back to a height of 0. And so what happens is the graph traces out this wave-like pattern to represent that. Okay? So you can see all three phenomena going on at the same time, right? My point is moving around the circle. Look at the little red segment on the left. That's exhibiting just good old repetitive up and down motion. And the right side is tracing out a wave. See all three working together? Pretty neat. Okay? So, I tried to click on this little cosine button because I was hoping that it could graph cosine for me, but the little clicky-clicky thing doesn't work. So I assume this is some little editing it's updating for me. That's okay, we can do it by hand. So, I did. That didn't work either. Alright, so what I thought we'd do is let's just map out x, and we'll draw our own cosine wave, okay, on the board, and then I'll transfer it onto here. So, what is my x coordinate right now? My x coordinate for this flat point is 1, right? So you put your first dot here. Okay, let's go to 60 degrees. It's a little hard to do with the mouse. There, I got it at 60 degrees. What is my x coordinate right now? 0.5. It's right on the money. Okay? So that means at 60 degrees, I'm here. So like that. You don't have to draw this, just follow along with me. Okay, next stop is 90, the top of the circle. What's my x coordinate when I reach the top? My x coordinate is 0. Yes, it is. So at 90 degrees, my x coordinate is 0. Next stop is 120. What is my x coordinate? -0.5, correct? So at 120 I'm at -0.5. Next stop is 180, where my x coordinate is -1. Right. So 180 I'm at -1. Next stop is 240, where my x coordinate is -0.5. Next stop is 270, where my x coordinate will be what? The x coordinate is 0 on the y-axis again. So at 270 I hit 0. Next stop is right there at 300, where my x coordinate is now 0.5. And lastly, if I go full circle, I end up at the same x coordinate I started at, which was 1. So my wave looks a little different, right? My wave looks more like this. What once were peaks and valleys are now roots, x-intercepts. Okay? Is it a different graph? It sure appears different, but if you could see multiple cycles together, you would say they really don't look that different at all. Okay, so let's look at them together, side by side. In a more extended version, that was tangent. Let's delete that. Okay, let's put in cosine. Let's do sine first. Sine of x, nice thick pen width here. And let's do cosine of x. So sine x is in purple. Cosine x is going to be a mystery color. Let's see what it is. Lavender? Too close to purple. Somebody say a color. I heard green first. All right. A little hard to see. But my point in showing you this view is if you do multiple cycles going forwards around the circle and backwards around the circle, you get an extended wave. Okay? And you can see here they really aren't that different looking at all. In fact, if you slide the purple curve to the left 90 degrees, it is the same as your green curve. Or you could say you can move the green curve right 90 degrees, and it would match up well with the purple. Okay? This makes you want to write a brand new little theorem right here, doesn't it? How about some little rule like if I do sine x and cos x, the relationship with this is that if I take cosine x and slide it to the right 90 degrees, it will be a sine wave. Slide it to the right 90 degrees is written as x minus 90. So there it is, a brand new rule we could write down. There are so many of these, it's ridiculous. Stay tuned, in chapter 6 we'll have many, many more. Okay? So that's actually a brand new rule. Or you could write it this way. What would I have to do to the sine wave to get it to land on top of that cosine wave? I'd have to move it to the left, right? So you put a plus 90 there. Sliding a sine wave left 90 gives you a cosine wave. Sliding a cosine wave right 90 gives you a sine wave. Interesting little facts as we go. Okay, I would like you tonight to make one flashcard for sine wave. Okay? So it would look something like this. The front of your card would have a table with thetas and sine thetas. You should put in all the special angles, okay? 0, 30, 45, 60, 90, all the way up to 360, okay? For the right column, I suggest you use decimals. It's a little bit easier, but you would have 0, 0.5 instead of a half. Instead of root 3 over 2, that's 0.866. Okay? It's just easier to plot when you're dealing with decimals. Except I wrote that wrong. That's actually 0.707. The next one's 0.866. There we go. Sine 90 is 1. Go ahead and plot it out, and it would look like this. Just stop when you get to 360. This is called the first fundamental period. The fundamental period. Fundamental means you can't live without it. If you don't memorize this, you got nothing. You got to memorize this. That's the fundamentals. Okay? If you want to draw two periods, be my guest. That's just another version of this, starting from 360 and going to 720. Or you can draw a left-hand piece. Let's talk about the left piece. Okay, some people in the past have drawn this for me on the left side of their flashcard. That would be wrong. We said that sine is an odd function and has origin symmetry. You just made it an even function and gave it y-axis symmetry. Wrong pick. Okay? It should have been like this if you're going to do a period on the left. It needs to look like it can be flipped upside down. You know, or rotated, I mean. Okay. So anyway, if you decide to draw a second period on the left, at least get it correct. The back of your card, you can put all your nifty little facts about sine that we've been learning, right? Sine of 180 minus theta is the same as sine theta and so forth. Anything you want. Sine is an even function. Stuff like that. Sine is the y coordinate on the unit circle. Sine is y over r if you're not on the unit circle. You understand? Okay, do tomorrow. One card. Okay. We also mapped out cosine. We're going to do that card too, but I've already got some graphing stuff for you to do tonight. So we're going to do 4 graphing problems and 1 flashcard. All right, let's take a look at a transformation problem. because if you now have a new flashcard, we should be able to move it, flip it, stretch it, that sort of thing. Okay? All right. So I'm going to have you graph on graph paper. Four functions. You're doing those 4 problems over on the board there tonight. But I'm going to do an example for you of one that's sort of amongst the harder ones. So you have a harder one to look at. And the one I'm doing is y equals negative 3 sine of 2x plus 180 plus 1. Whoa. The only thing I didn't include is the kitchen sink. I didn't include a reflection over the y-axis. Everything else is there. I've got a horizontal compression, I've got a vertical dilation, I've got a reflection over the x-axis, I've got a left shift, and I've got an upshift. It's all there. The only thing that isn't there, like I said, is a flip it backwards sort of thing. Okay, so how would you graph this? Well, I can tell you now, you can punch in your calculator and you'll get the graph. But that's not what I mean. I mean using transformations. Okay, so it's pretty apparent that we're talking about a sine graph, right? That's no surprise. It says sine right there. So we identify the parent function. It's y equals sine x. Sine x, whenever I draw it, I feel like I'm writing the English letter n, because sine looks like this. And if I had to compare that to writing an English letter, it feels like I'm drawing a capital N, sort of. Capital N looks like this. It's the closest letter I could think of to help me remember it. Kind of feels like you're writing an N, except it's more rounded. Some people say it looks like an S for sine. That makes sense. I'll let you decide how you want to memorize it, but it definitely starts at the origin, goes up, down, up, and hits the axis again. Okay, you want at least 5 points for reference. Remember on our other note cards we had 3. We had -1, 1, 0, 0, and 1, 1. Remember that? And so forth. So we're going to be using these 5 points for reference. They are 0, 0, 90, 1, 180, 0, 270, -1, and 360, 0. I'll write those. I said them, so I'll write them. 0, 0, 90, 1, 180, 0, 270, -1, and 360, 0. This is, of course, in degrees. You could also call them 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So I'm going to try to transform these 5 points and then connect the dots in the end for my transform graph. All right? All right, moving on. So I've got it in degrees, okay? Just understand you can also use radians, 0, pi over 2, pi, and so forth. All right, so this is a max height of 1, and least value is -1. Now there are more periods, but I'm only drawing the fundamental period. If I can draw this, then I can extend it later and make it more, fleshed out. Okay, so what are my transformations? There's a lot of them here. Anyone volunteer a transformation? What's going on here? What do you see? Look at my equation. I got -3 sine 2x plus 180 all plus 1. Lots of things going on here. Don't graph on the calculator. Graph it by hand. What does the plus 1 mean at the very end? What is that? Okay, up 1. Got it. Okay. What does the negative here mean? Is that the upside down flip or is that the backwards flip? This is reflection over the x-axis, okay, because it's going to be upside down. All right, negative on the outside means upside down. Okay, so reflect over the x-axis. Okay, what does the 3 itself mean? Okay, it's definitely vertical. Notice I'm not multiplying that 3 against an x, right? So it's nothing horizontal there, but that is a vertical something. Now 3, is that bigger than 1 or less than 1? Bigger than 1. Okay, so it's going to be a vertical stretch. vertical stretch. Okay, let's get on the inside here. I don't like the way it's written. I really don't. I don't like the fact that it says 2x plus 180, because when I first looked at this, I thought, ooh, left 180. But no, that's when it says x plus 180. It doesn't say x plus 180, does it? Why don't we factor out the 2 so we can properly understand this? This is 2 times x plus 90. There we go. So it's not a shift to the left by 180. It's a shift to the left by what? 90, yes. So this means left 90. And then what does the 2x mean? 2 implies we're multiplying the x's, we're multiplying the argument by 2. That means it's going to be a horizontal dilation of some kind. Is it a stretch or compression? What is that? It's counterintuitive. When you're on the inside, multiplying by 2 actually shrinks it. It is a horizontal compression. I know, it's tricky. It's tricky. So this is a horizontal compression. Wow. Lots of things to think about. But I need to do them in this order. Dilate, reflect, translate, dirt. Okay? So first thing I'm going to do is take care of my dilations. That's the 3 and the 2. Okay? And then I'm going to take care of my reflections. I've only got one. I'm going to turn it upside down. Okay? Then I'm going to take care of my left shift 90 and my up shift 1. And you want to do them in that order, okay? So let's give this a try. Now I can move the graph along, or I can just watch these 5 points transform and then connect the dots. I choose that. So first thing I'm going to do is my vertical stretch. I'm going to multiply all the y coordinates by 3. Okay, so let's rewrite our points. These are the original points for y equals sine x. What would happen if I did y equals 3 sine x? You would triple all the y coordinates. So what would they look like? 0, 0 still. 90, comma 1 would become 90, comma 3 now. You're tripling all the y's. 180, 0 stays as 180, 0. 270, negative 1 is now 270, negative 3. And 360, 0, that's not changing. I'm multiplying the y's by 3. That's my first transformation. Excuse me. Now I need to do a horizontal compression by a factor of 2. So what I need to do now is shrink all my x's to half size. Okay? So let's make all the x's half size. This will be the table for 3 sine of 2x. Okay? 0, 0 doesn't change. 93 becomes 45, comma 3. 180, 0 becomes 90, 0. 270, negative 3 becomes 135, negative 3. And 360, 0 becomes 180, 0. My entire graph will be a compressed sine wave. So it will not require 360 degrees to do this first cycle. It just collapsed down to the first point at 0, and the last point is at 180 now. The whole thing has been compressed inward. You'll see in a moment. Okay, next are the 2 shifts. You can apply those simultaneously. If you're going to go left 90 and up 1, you can simply subtract 90 from each angle and add 1 to each y coordinate. Okay, so let's do that. This will be the final list of points. I forgot to reflect. I cannot translate until I reflect. Okay, I need to do the reflection. Sorry about that. Forgot about that. I need to do the negative 3 now. What does this do? This reflected over the x-axis, so it's going to effectively negate all my y coordinates. Okay, can't translate till I do that. So I have 0, 0, 45, 3 is now 45, negative 3. 90, 0 stays. 135, negative 3 is now 135, positive 3. And 180, 0 stays. Okay, final function, here it is. Moment of truth. We understand this means a left shift 90. So our points are all going to lose 90 degrees. So this will be negative 90. This will now be negative 45. This will now be 0. This is now 45. and this is now 90. So I just subtracted 90 from every single x. I now need to add 1 to every y value to create an upshift. It becomes 1, negative 2, 1, 4, 1. If you plot these and connect the dots, you've got your graph. All right, so let me do that. You guys can use graph paper. I just usually make these all 90s. I don't even need to go to 360. I don't even need to go to 180. Everything falls right between negative 90 and 90. Maybe I've exaggerated too much. Let me redo my axis here. This is something you kind of have to do, when you're graphing these, you have to decide on a good axis. How about we just go from negative 180 to positive 180. We don't need all that extra dead space. There we go. For y coordinates, it looks like everything falls between negative 2 and positive 4. So obviously my scales are a little different. My y-axis is by 90s, my y-axis by 1s. And let's just plot. Okay, so negative 90, comma 1 would go right here. Negative 45, comma 2 would be right here. 0, 1 would be right here. 45, 4, let's see, this isn't quite right. Yeah, 45. Oh, I have this point in the wrong spot, that's why. This point here should have been at negative 2, thank you. The second one I drew should have been right here, thank you. 45, comma 4 is right here. And lastly, 90, comma 1 is right here. And then you can connect your dots. I like to use 5 reference points because otherwise I find it hard to connect them in the end. But not now, this is simple. I got it. Okay, so the whole graph is raised up a space. It's no longer centered well on the x-axis. It's up now. The range is different, isn't it? The range is between negative 1 and positive 4. I think I need to make this point a little higher too. There we go. This point a little lower. Didn't do a very good job, did I? That's why graph paper helps. Try to make these rounded, not too sharp. Okay, these are not like absolute value functions, but they're not as sharp as parabolas, so they're kind of in between. Your calculator could have given you that in 3 seconds, but you would have learned nothing at all. So if you use your calculator tonight, you will learn nothing at all. Do it by hand, check it on the calculator. If you want to flesh it out and add more periods, it's just literally copy and paste. Just draw another one just like it right next to it. Maybe one over on this side. Try to do better than I just did. So you're doing 1 flashcard and 4 graphs. Use graph paper or I will not accept it.